Now let us introduce a simple audio classification work. This work was published in year 2001 in IEEE Translations on Speech and Audio Processing, which is one of the most important journal in the speech and audio and signal processing. And the author you can see here, one of the author is quite famous, Professor C.C.J. Guo. You may still remember this name when you look at the material about the wavelength texture feature. And this work is entitled Audio Content Analysis for Online Audiovisual Data Segmentation and Classification. They propose a system that can discriminate various types of audio signals based on very many audio features. And this is the overview of this work. So given an audio signal, they will first extract several features including energy function, average zero crossing rate, fundamental frequency, and spectral peaks, and so on. And then they will detect the segment boundary and then classify each audio segment into several types, including settings with music component or without music component. And for those segments with music component, they further classify them into harmonic environmental sound, pure music, song, speech with music background, and environmental sound with music background. For the segment, audio segment without music component, they will classify them into pure speech or non-harmonic environmental sound. And then after some post-processing, they get the audio scene segment or index. And this work was one of the most early audio analysis work. And you can see this paper has been cited many times. Based on some characteristics, they can do such work. First, they take into account hybrid types of sound, which contain more than one kind of audio component. And before this paper was published, fieldwork takes the audio signal of so many types. And then this would be one. This would be the one of the first works to handle hybrid types of audio signals. They put more emphasis on the distinction of environmental sound. Before this work, fieldwork focus on environmental sound, but it's essential in many applications such as post-processing of film. They will integrate many features to do audio classification, and it's low complexity. And the proposed method is generic and model-free, so they don't propose a parametric model or probability model. They use several rules and convention to do audio classification based on several types of audio features. The proposed system can be used as a tool for segmentation or indexing of radio and TV programs. The first feature they use is zero crossing rate. Okay, and here we show 4 examples about the zero crossing rate in different types of audio signal. The first type is speech. So we can see there is large variation in the speech signal in terms of the ZCR. The second one is piano. So we can see here for a music signal, the zero crossing rate fluctuate just slightly, much fewer than the speech signal. The third one is chime. Okay, that is chime, C-H-I-M-E. That's a kind of sound effect, and we can see the evolution of the ZCR is quite unique. The first one is the footstep. Okay, the people walking and the footstep, and we still can see the zero crossing rate fluctuate a lot. So this is more similar to the speech. The second feature is the fundamental frequency. As we mentioned above, fundamental frequency is highly related to pitch, and they want to use such feature to distinguish between harmonic from non-harmonic sound. So sound from most musical instruments are harmonic. Okay, and the speech signal are harmonic and a non-harmonic mixed sound, because voice speech is harmonic, but on voice speech like st, k, they are non-harmonic signals. And the most environmental sound are non-harmonic. Therefore, they use the fundamental frequency to roughly discriminate harmonic and non-harmonic, and then they can do finer classification if they incorporate more audio features. So these are two examples showing the amplitude evolution. Here, the first one is the trump. Okay, TRUMPET. This is one kind of musical instrument, and we can see the amplitude evolution based on in terms of different frequency. There are some clear valleys. Okay, that means this audio signal is harmonic and has clear fundamental frequency. The second example is the applause. Okay, applause like this. Okay, and the applause has no fundamental frequency, has no clear fundamental frequency, and it would be a non-harmonic audio signal. Based on fundamental frequency, we can make some observation. All maxima in the spectrum are detected as potential harmonic peaks. Okay, so we can first detect the peaks, and then we check among locational peaks, and to check whether they have sharpness, amplitude, and the width value satisfying certain criteria. If all conditions are met, then the short time fundamental frequency value is estimated as the frequency corresponding to the greatest common divisor of the location of harmonic peaks. Okay, otherwise this value is set to 0. So the essential idea here is quite similar to what we have mentioned before. We use autocorrelation before, but here they use the greatest common divisor of this value of the location of harmonic peaks. Okay, if we can clearly find the greatest common divisor, then we can say that they have fundamental frequency. They have clear fundamental frequency. And these are 4 examples showing different sound effects and the corresponding fundamental frequency. The first one is a musical instrument trump. Okay, trump. So we can see in most of the time the fundamental frequency are located at several levels, like here, and here. Okay, and the second sound effect is speech. For speech, there are some fundamental frequency around here. Okay, around here, and the third one is running. Okay, the sound of running. So we can very clearly see that there is no clean fundamental frequency of such audio effect. And the final one is left. So people laughing, and when people laughed, they issue voice sound. So we have clear fundamental frequency. And in addition to see whether there is fundamental frequency, we will also check the frequency. Okay, the frequency value of the fundamental frequency. Okay, and we can see for laughing, we have maybe 1 or 2 fundamental frequency. For speech, we also have several one. But for musical instrument, we may have several fundamental frequency at different time instance. Based on the extract audio features, the first step is to segment the given audio signal into appropriate audio segments. The method here is to apply two adjoint sliding window. And you can see that this is a big sliding window, but we divide it into 2 parts. The first part, we will calculate the average audio features for the first part, sliding window. And we also calculate the average audio features for the second window. And then we will calculate the difference between these 2 consecutive windows. And basically, this is the same way for us to detect the video sharp change. Okay, in video sharp change, we just calculate for example, the color histogram of a video frame, and then we compare the color histogram of this video frame with previous video frame and check the distance, whether the distance is larger than a threshold or not. And right now, for audio segmentation, they also do the same thing, but based on audio features. These are 2 examples based on if we calculate the difference between short time energy function and the short time fundamental frequency. For these 2 examples, the x-axis means the time, the y-axis means the energy amplitude. So the first part here is the speech signal, and then the environmental sound, and then music, and then speech again. So we can see based on energy distribution, we roughly can discriminate speech, music, and speech according to how the energy involved along time. Another example is based on the fundamental frequency. For speech, okay, the fundamental frequency will change significantly along the time because we human speech have voice speech and unvoiced speech. And for singing, if we human do singing, then the fundamental frequency will change. Usually, the fundamental frequency become higher when we sing. And based on energy function and the short time fundamental frequency, we can find the boundary between different audio segments. After dividing signals into segments, we now can do audio classification. The step is that in the following. They first detect silence. Okay, if the short time energy is continuously lower than a threshold, or if most short time average zero crossing rate is lower than a threshold, then we can classify this audio segment into silence. Okay, so first we just remove silence, and then the second step is we separate the sound with and without music component. Okay, by detecting continuous and stable frequency peaks from the power spectrum. Then based on the threshold for the zero ratio at above 0.7, if a given audio segment has more than 70% zero ratio, then we will say that it's a pure speech or non-harmonic environmental sound. Otherwise, it belongs to other types of audio. Okay, so the second step is workable based on the frequency peaks, stable frequency peaks. Okay, because we have already known that for music component, they have more stable frequency peaks. Okay, and here is we calculate the zero ratio. Okay, so on the other hand, for pure speech or non-harmonic environmental sound, there are more zero ratios. Okay, they have they don't have stable frequency peaks like that. So based on such method, we can discriminate sounds with or without music component. The third step is detect harmonic environmental sound. If the fundamental frequency of a sound clip change over time, but only with several values, then it would be a environmental sound. Okay, because usually environmental sound is not so complex. Okay, they may be harmonic, but they usually just belong to several different pitch. Okay, but if it's a music, and because music have various pitch, and they all have a different fundamental frequency. Therefore, if the fundamental frequency of a given sound change over time, but with only several values, then we will say that this segment should be a harmonic environmental sound. And then the next step is distinguishing pure music. Based on statistical analysis of the zero crossing rate and the short time spatial flux curve, then we can estimate the degree of being harmonic, the degree of fundamental frequencies concentration on certain value during a period of time, and the variance of the average zero crossing rate, the range of amplitude of the average zero crossing rate. So based on these values, this statistic of audio features, we can discriminate whether it's a pure music or not. Because at the previous step, we have already discriminated audio segment with and without music component. And for that, with music component, we will discriminate further. Discriminate them into harmonic environmental sound or music. And then we will distinguish sounds and separate for that without music in the background. We will separate the speech and the environmental sound with music background, and then distinguish pure speech and or classify non-harmonic environmental sound. And basically, if you are interested in the technical detail of this paper, please refer to this paper. And basically, for each these steps, they just define some threshold to they define a set of rules to classify a given audio segment into one of the audio type. Okay. In the evaluation, they do several experiments. The first one is the accuracy to discriminate silence, the sound with music component and without music component. And there are a few samples. And right here, we can see the correct sample, the false alarm. Okay. But basically, you can just take these values as for the reference, because the accuracy for different audio signal may be very content dependent. That means if you try different audio, you try different data set, then the experimental result may be totally different. Okay, so this is just for your reference. At that time, because this is one of the most early audio analysis work, so they just use simple method based on conventional convention or some heuristic rules, they can and based on a limit set of audio sound, they can achieve such accuracy. But this is just for your reference. Today, if you just do the audio classification like this, then I guess you cannot detect audio segment, or you cannot classify audio signals very accurately. And here are several audio types, including pure speech, pure music, song, speech with background music, sound effect with background music, harmonic sound effect, and then non-harmonic sound effect. Okay, and then there are hundreds of samples, and the report accuracy here look quite so good, but this is also just for your reference. And if please refer to the following reference, of course, especially the first paper, although it was published in more than 10 years ago. But this paper is quite famous, and it's easy to read, and it's good for you to briefly understand the audio content analysis. The second one is also quite famous, published in 1998. And the paper we just mentioned here was published in year 2001. Okay, one of the most early work to classify various types of audio signal.